All right, so we're picking up in the notes where we left off, and we left off on example 3, and I'm going to try to put all the writing on here. We'll see how it goes. So it says, find the first 4 non-zero terms and the general term for the Taylor series. Now this is going to be important because it's not a polynomial, so they didn't give us a specific degree. That means they want the entire series. They want it to go on for infinity. Where f of x is e to the 5x. So I'm going to say f of x is e to the 5x. And I'm just going through and I'm getting my function. And I'll do a few derivatives here. I'm just going to do the first 3. So the derivative of e to the 5x is e to the 5x multiplied by 5. So I can rewrite that as 5 e to the 5x. The second derivative would be 5 e to the 5x multiplied by 5. So I'll go ahead, instead of writing that as 25, I'm just going to write that as 5 squared so you guys can see the pattern. The third derivative is going to be itself, so 5 squared e to the 5x multiplied by the derivative of the exponent, which is 5. So that's 5 to the third e to the 5x. So just a little reminder there, the derivative of e to the x is itself, and so each time I was just doing the chain rule and I was multiplying by the derivative of the exponent. So next, I know it's centered at c equals 2, that means that I have to evaluate each of these for 2, and then I can go through and write down what my polynomial, or what my series is going to be. So that's e to the 10. The first derivative is 5 e to the 10. The second derivative is 5 squared e to the 10. The third derivative is 5 to the third e to the 10. All right, so now I can go ahead and write it out, and that's going to give me, I've got my first, I'll go ahead and write it down here. So e to the 10 plus 5e to the 10 times that center part, so x minus 2, plus 5 squared e to the 10 times x minus 2 squared over 2 factorial, plus 5 to the third e to the 10 times x minus 2 over 3 factorial. And then the pattern would continue, so it's going to be 5 to the n, e to the 10 will always be there. Sorry, this was x minus 2 to the third. X minus 2 to the nth over n factorial. And then I'm going to show that it keeps going. And this dot 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 right here and this dot 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 right here are important because this is showing, you know, I'm following the pattern until I get to the nth term, and then this is showing it's a series, it's going to go on forever. So it's important to write it this way because we're talking about a series, not a polynomial. All right, for example 4, it says that this is the original function and it wants us to find the derivative of the function, and it wants us to evaluate the derivative when x equals 0. So if that's our original function, the derivative of 1 is 0. The derivative of x is 1. And then with this, I'm going to multiply that in the front. So 2x over 2 factorial. 3x squared over 3 factorial. And then dot dot dot. N times x to the n minus 1 over n factorial. So there is our derivative right there, and if you simplify this a little bit, we know that 2 factorial, or let's just think about how our factorials work. So 3 factorial is 3 times 2 times 1. So if I cancel out 3 with the 3 in the front, then that would leave a remainder of 2 factorial. If I cancel out 2 with 2 factorial, because 2 and 2 factorial are the same, then I can do that. If I think about n factorial, that would be n times n minus 1 times n minus 2 times n minus 3 all the way down. And so if I cancel n with the n, then that's going to leave n minus 1 factorial. And so what I really have here for my derivative is I have 1 plus x squared over 2 factorial, and then x to the n minus 1 over n minus 1 factorial, plus dot dot dot. So if you compare this with the first one, these are the same. And if you recognize them, you might see that these are both the function e to the x, which makes sense because e to the x is the only function I think that we know of where the original function and its derivative are exactly the same thing. So I'm going to say f of x and f prime of x both equal e to the x. And then if I want to go ahead and take the derivative and evaluate it for 0, just plug 0 into all the x's, I'm going to find that that equals 1. All right, example 5. So if we look at this one, they give us this to start with, and then they say they want capital F of x, and that's going to be the integral. So we're going to go ahead and find the integral of 1 plus x squared over 2 factorial and we're gonna plug in 0 to get 1. That's gonna help us figure out our c value. If you guys remember that usually that point they give you is to help you find c. So the integral of 1 is x. The integral of x is 1/2 x squared. And then we're going to have a 1 over 2 factorial in the front. The derivative of x squared would be 1/3 x to the third. So I'm going to take this bottom part and multiply it by 3. And then get an x to the third. Keep 1 over 3 factorial. Then I'm going to multiply this by 1/4 x to the 4. So for this one, I'll keep the 1 over n factorial, and that's going to be multiplied by n plus 1 times x to the n plus 1. And of course, we have a plus c on the end. So if you look at this, if we were to simplify this, I can say that this is x plus x squared over 2. 2 is the same thing as 2 factorial, so I'm going to go ahead and write 2 factorial, plus x to the third. 2 factorial being multiplied by 3 is the same as 3 factorial, plus x to the fourth over 3 factorial multiplied by 4 is the same as 4 factorial. And then I've got x to the n plus 1. N multiplied by n plus 1 is the same as n plus 1 factorial. Right? And then we have that plus c on the end. So then we have to picture what will happen if I take 0 and I plug it in for all of the x's, and then I say that the equation equals 1. So I'm plugging 0 into all of the x's, I say this equals 1. So if I plug in 0 here, 0 here, 0 here, all of these 0 out, 0 out, 0 out, except for the c, and then this equals 1, and so that means that my c value must be 1. And typically when we put that 1, we put it right in the front. All right, so again, you'll notice this is the same as this, and hopefully you'll recognize that these, this function again, that f of x, lowercase f of x and uppercase f of x are both e to the x. And so we were doing it both ways. We were saying if I take the original function and then take its derivative, they both happen to be e to the x, or if I take the original function and then take its antiderivative, they both happen to be e to the x. All right, so you might have recognized those because that's one of those 4 Maclaurin series or polynomials that we looked at where there's like a specific little trick to them, or you could just know it because it's the only situation we know of where the derivative and the function are the same, or the antiderivative and the function are the same. All right, so next it says to give the Maclaurin series for sin x, so that's one of the ones that we learned. And I'm going to go ahead and write that out. And then it says to take its derivative, and you'll see that it's the Maclaurin series for cos. So I'm going to say the derivative of sine. So the derivative of x is just 1. And then I'll bring this to the front, so 3x squared over 3 factorial. And then 5x to the 4th over 5 factorial. And then we'll go ahead and take this exponent, move it all the way to the front. So 2n plus 1, and subtract 1 from it, 2n. And so what you'll notice here, the derivative of sine is cos. So we've got 1, and then 3. You can say that the 3 cancels with 3, and that leaves us with 2 factorial. So x squared over 2 factorial. You can say the 5 cancels with 5, and that leaves us with 4 factorial. And then the 2n plus 1 would cancel with 2n plus 1, and that would leave us a 2n factorial. And if you compare this with the Maclaurin series that we learned, you'll see that this really is what the Maclaurin series for cos x is. So kind of cool, like a little proof there, kind of. All right, so it says down here, and we kind of did this already, that you can manipulate these special series to find other series by using these techniques. So you can substitute the series in for x. You did that on the last worksheet a couple times, just kind of using it to like find a limit so you could avoid L'Hopital's. You might multiply or divide the series by a constant or a variable. You could add or subtract 2 of the series or a term to a series. You can differentiate or integrate to go back and forth like what we just did. And it says it may change the interval of convergence, so be careful to watch out for that. Not the radius, but just the interval of convergence. And then it says recognize a series as a sum of a geometric power series, which you're going to learn soon. All right, so if you look at your next page of notes, we're going to look at example 7. So it says find the interval of convergence for f and f prime, and then the integral of f. So if I look at this, you can write out all the terms, but it's a little bit easier just to focus on this part right here, because when we find that interval of convergence, that's the only part we look at anyway. So I'm going to say, I can divide this into 3 spaces. All right, so for the first one, f of x was x to the n over n. And so I can see with this that the center would be 0, because that would be like an x minus 0 in parentheses. And I'm going to go ahead and do the ratio test on this. So the limit as n goes to infinity of x to the n plus 1 over n plus 1. And then I can go ahead and multiply that reciprocal up. So for this one, I'm going to go ahead and rewrite it as x to the n times x to the 1, and the x to the n's cancel. So I'm finding the limit as n goes to infinity of x times n over n plus 1. And since the n's are the same size, that means that my limit here would be x. So since the ratio test tells you that it converges if this is less than 1, then I know that my radius of convergence is 1. So my center of convergence was 0, my radius of convergence was 1, so that makes my interval from -1 to 1, and I just have to check those ends, the -1 and the +1, and see what works for those. And well, this is the one that takes up the most space. I'm going to go ahead and erase this line. Okay, so I'm going to go ahead and check it for -1. So when I check this, I'm going to say that I've got -1 to the n over n. And as you can see, this is an alternating series test. So we have two conditions. We have the limit as n goes to infinity. We ignore the alternating part, and we just say 1 over n, and it should equal 0, which is true. And the second condition is 1 over n plus 1 is less than or equal to 1 over n, and that condition is also met. So that means that -1 in the interval is included in the convergence, because it converges at -1. Then I also want to check +1, so I'm going to say I've got 1 to the n over n, and this right here, that would always be 1, so this is 1 over n. That is a harmonic p series. That's a p series where p equals 1, and that means that it diverges. So we're going to have a parenthesis there. Okay, hopefully I can take less space for these other ones. All right, so my derivative, I'm gonna write it up here, if f of x was x to the n over n, then my derivative, I'd take this, I'd move it to the front, so n times x to n minus 1, still divided by n. So for my derivative, I can cancel out those n's, and that's just taking x to the n minus 1. And if you look at this, hopefully you're recognizing that this is a geometric. And so we know that geometric series converge if the r value is less than 1, and in this case your r is x exactly. So if x is less than 1, and so that means that our interval for convergence here is again from -1 to 1, because we had a center at 0, that's x minus 0 if you put it in parentheses, and we had a radius of 1. So our interval is from -1 to 1, and then we just have to go back and we have to check for -1 and check for +1. I'm going to write my work real small here. So when I check for -1, that gives me -1 to the n minus 1. This is a geometric series where the r value is -1, and so that's going to diverge. When I check for +1, and I have 1 to the n minus 1, that's a geometric series where the r value is 1, so again that diverges. So here we're going to say that our interval is from -1 to +1, and we are not including either of those ends. Alright, the last one, oh gosh, this one's probably going to have to be done on a separate sheet of paper, I'm really sorry. So the last one is the integral of f of x. So we have to take this, and so I'm going to add 1 to the exponent. So I had 1 over n to start with, and now I added 1 to the exponent, and I'm bringing it down to the front. Alright, so this one is going to require a ratio test, which is why I just realized I don't have near enough room. So again, on this one, the center is 0. I can see that because there's nothing in the parentheses with that one. And so now I just need to find my interval. So I've got the ratio test. So the limit as n goes to infinity of x to the n plus 2 over n plus 1 times n plus 2, and then x to the n plus 1 over n times n plus 1. And I'm going to multiply by that reciprocal, So here I can go ahead and split these apart. So that's x to the n plus 1 times x to the 1. And I'll notice that x to the n plus 1 will cancel, and this n plus 1 will cancel with that n plus 1. And so we end up getting that the limit as n goes to infinity, and we'd have x and n left over on the top and n plus 2 left over on the bottom. And so the limit as n goes to infinity, the n's are the same size, they're going to cancel, we're just going to get x. And again, the ratio test converges if this is less than 1. So that tells us here that again, if our center is at 0 and our radius is 1, our interval goes from -1 to +1. And so now we just have to go back and check those two endpoints to see. So I'm going to check -1. So I want to see what happens. I've got -1 to the n plus 1 over n times n plus 1. And this right here is an alternating series test. So the first condition that we check is to make sure the limit as n goes to infinity, and I ignore the alternating part, I'm just looking at this part. I want to make sure that limit is 0, which is true. And then I want to make sure that if I add +1 to each of my n's, that is smaller than if I don't. That is true. So we know that it is converging at -1 because this passed both of the conditions for the alternating series test. So I'm going to go back up here and I'm going to put a bracket right there. Okay. Then I can go ahead and check +1. So that leaves me with 1 to the n plus 1 over n times n plus 1. So this top part over here is always going to be +1. So this is really 1 over n times n plus 1. And I'm going to go ahead and do a direct comparison test, and I'm going to compare this with 1 over n squared. And I know that 1 over n squared, that's a p series where p equals 2, and I know that that converges. So for the direct comparison test, I've got 0 is less than 1 over n times n plus 1, and that's less than or equal to 1 over n squared. And since this converges, then by the direct comparison test, I can say that this one converges as well. So I'm going to go back up here and say that the interval is from -1 to +1, including both of those n's. All right, so what we were saying on that previous page about how when you differentiate or integrate the series, it might change the interval of convergence. We saw that. So we saw that the endpoints were included or not included, but it didn't change the radius. You'll notice that the radius on all those intervals was 1. And so that's a good thing to make note of. All right, and then for the last 3 examples, I'm going to put notes on the website for you. Okay?